Hello, in this lecture we'll find out the area of the green shape. In the drawing we have a circle. We know that the radius of this circle r equals to 2, and also we have inside this circle peripheral angle ACB. This is peripheral angle ACB that is equals to 70 degrees in its size. In addition, we have in the drawing, this is point P, that is a common external point in relation to this circle. And for the common external point P, we have two tangents to this circle, tangent PA and tangent PB. Our mission is to find out the area of this green shape. The center of this circle is here at point O, so we join points O and B together by a straight line. So what is the definition of line segment OB? Point O is the center of the circle, point B is the point of the circle itself. This is exactly the definition of a radius. So OB is the radius of this circle, that is equal to 2 units in its length. So we can implement here rule 1. According to rule 1, a tangent to the circle is perpendicular to the radius drawn to its point of tendency. So in the drawing we have a circle, and we have also tangent AB that is tangent to this circle at point M. Point M is the point of tendency of tangent AB with this circle, and we have also the radius OM that is equal to R. The radius OM is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. If AB is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to this rule 1. So we can implement rule 1 in our drawing. Why? Because in our drawing we have the radius OA of this circle that is drawn to point A, that is the point of tendency of tangent PA with this circle. Whenever you have a radius that is drawn to the point of tendency, then tangent PA will be perpendicular to the radius AO. If PA is perpendicular to AO, it means that this angle equals to 90 degrees. According to rule 1, of course. Likewise, according to the same rule 1, we have here the radius OB that is drawn to point B, that is the point of tendency of tangent PB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent PB will be perpendicular to the radius PO. If PB is perpendicular to BO, it means that this angle equals to 90 degrees according to the same rule 1. So in the next step, I will present to you a new rule, and we will implement the new rule in our drawing. The new rule is rule 13. According to rule 13, a central angle is twice as large as the peripheral angle subtended on the same arc. So I repeat again on rule 13. According to rule 13, a central angle is twice as large as the peripheral angle subtended on the same arc. So in the drawing we have a circle. Inside this circle we have peripheral angle ACB. Peripheral angle ACB equals to theta degrees in its side, and is subtended on this arc AB. In addition, we have in this drawing the central angle AOB that is subtended on the same arc AB, and therefore the central angle AOB will be twice as large as this peripheral angle ACB. And because of the fact that the peripheral angle ACB equals to theta, therefore the central angle AOB that is subtended on the same arc RKB will be equal to 2 theta. So we can actually implement all 13 in our drawing. Why? Because in our drawing we have peripheral angle ACB. This is peripheral angle ACB that is equal to 70 degrees in its size and is subtended on this arc RKB. And therefore the central angle AOB that is subtended on the same arc RKB will be twice as large as this peripheral angle. And this peripheral angle ACB equals to 70 degrees, therefore the central angle AOB that is subtended on the same arc will be equal to 70 degrees times 2, that is 140 degrees. In conclusion, found out that the central angle AOB equals to 140 degrees in its size. In the next step, we will join points O and P together by a straight line. By joining points O and P, we can do two right triangles, the right upper triangle AOP and the right lower triangle BOP. So in the next step, we'll prove that those two right triangles can go into each other. The right upper triangle AOP is congruent to the right lower triangle BOP. Okay, so I'll write it down. We'll prove that the right upper triangle AOP is congruent to the right lower triangle BOP. So why those two right triangles can go into each other? First of all, side AO of the right upper triangle AOP is equal to side BO of the right lower triangle BOP. Because both of them are the radii of this circle, therefore they are equal to each other. So write it down. Side AO is equals to side BO. They are both equal to R, the radius of the circle, that is equal to 2. AO equals to BO equals to 2. In addition, side OP is a common side that belongs to both triangles, so you can write down that OP equals to itself is a common side that belongs to both triangles. And finally, side PA of the upper right triangle AOP is equal to side PB of the right lower triangle BOP. PA equals to PB according to rule 2. So I repeat quickly on rule 2. According to rule 2, the lengths of two tangents from a common external point to a circle are equal. In the drawing we have a circle, and we also have the common external point, point P. From the common external point, point P, we have two tangents to this circle, tangent PA and tangent PB. And according to this rule 2, they are equal to each other. That is to say, PA equals to PB. We actually can implement rule 2 in our drawing. Why? Because in our drawing we have the common star point P. From the common star point P, we have two tangents to this circle, tangent PA and tangent PB. And according to rule 2, they are equal to each other. That is to say, PA equals to PB. So, PA equals to PB according to rule 2. In conclusion, we found out that all the three sides of the right upper triangle APO are correspondingly equal to all the three sides of the right upper triangle PBO. Therefore, those two right angles can go into each other according to side rule. And for the fact that those two right angles can go into each other, we derive that those two angles are equal to each other. That is to say, angle AOP angle AOP in the right upper triangle AOP is equals to angle BOP in the right lower triangle BOP. Angle AOP equals to angle BOP. So if we define one of those two angles as alpha, if this angle AOP equals to alpha, then the other angle must be also equal to alpha because they are equal to each other. So this angle also must be equal to alpha because they are equal to each other. So alpha plus alpha is in total this big angle. Alpha plus alpha equals to this big angle, and we already found out that this big angle is equals to 140 degrees in its size. So in conclusion, you can write down that alpha plus alpha equals to 140 degrees. Alpha plus alpha equals to 140 degrees. Alpha plus alpha is 2 alpha, that is equals to 140 degrees. We divide this equation by 2. And finally we get that the missing angle alpha equals to 140 degrees over 2 is 70 degrees. So actually, this is the missing angle alpha that equals to 70 degrees in its size. And this angle alpha is equals to 70 degrees also. So in the next step, we'll focus on the right upper triangle AOP. In the right upper triangle AOP, it is very easy to see this right triangle AOP, right upper triangle AOP, tangents 70 degrees is equals to AP over AO. Repeat again, in the right upper triangle AOP, tangent 70 degrees equals to AP over AO. Tangent 70 degrees is equals to 2.75. So 2.75 is equals to AP. AP is the missing side, so we leave it as it is, over AO. AO is the radius of this circle, R, that is equal to 2, therefore we will substitute AO by 2. In conclusion, we found out that 2.75 equals to AP over 2. Here we will multiply this equation by 2, and we will get that AP equals to 2 times 2.75 is 5.5. In conclusion, we found out that the missing side AP is equals to 5.5 units in its length. Side AP equals to 5.5 units. I repeat again that our mission is to find out the area of this green shape. So what is the area of the green shape? The area of the green shape equals to the area of the upper right triangle AOP plus the area of the lower right triangle BOP minus the area of sector AOB. This is sector AOB. Repeat again that the area of the green shape in total is equals to the area of the upper right triangle AOP plus the area of the lower triangle BOP. Actually, the area of the upper right triangle AOP plus the area of the lower triangle AOB will give us the area of this quadrilateral AOBP. And the area of quadrilateral AOBP minus the area of this sector AOB will give us exactly the area of this green shape, that is the area that we are looking for. So here the rounded line above AOB is the sign for a sector. It means sector AOB. The square brackets is a sign for the area, so in total this expression means the area of sector AOB. Okay. So in the next step I'll explain to you the concept of a sector. What is a sector? A sector is a part of a circle. It is a portion of a circle. Here we have a circle, and the green shape AOB is a sector. So sector AOB consists of two radii. The first radius is AO and the second radius is BO. We can also say that sector AOB consists of two legs. The first leg is AO and the second leg is BO. And it is also consists of arc AB, that is between those two legs, AO and BO, or between those two radii of this circle, arc AB. And also it consists of angle theta, that is the angle between those two radii, of the angle between the legs AO and BO of this green sector, sector AOB. And what is the area of this sector AOB? The area of sector AOB equals to the area of the circle that contains the sector, that is pi r squared, times the angle between the legs of this sector, that is theta, over 360 degrees. Repeat again, the area of the grid sector AOB equals to pi r square, that is the area of the circle that contains the sector, times the angle between the legs of this sector, that is theta over 360 degrees. So pi r square times theta over 360 degrees is the area of this sector, sector AOB. Okay. So the area of the green shape equals to the area of the upper right triangle AOP plus the area of the lower right triangle AOP minus the area of sector AOB. But because of the fact that we have only found out that those two right triangles can go into each other, we can they have also the same areas. So we can substitute the area of this right triangle BOP by the area of the right upper triangle AOP because they are equal to each other. They have the same areas. So we substitute the area of the right lower triangle BOP by the area of the upper right triangle AOP because they are equal to each other. So the area of the green shape in total will be equal to the area of the upper right triangle AOP minus the area of the lower right triangle BOP. So we substitute the area of the lower triangle BOP by the area of the upper triangle AOP because they are equal to each other. Minus the area of sector AOB. The area of the upper right triangle AOP plus the area of the upper right triangle AOP is 2 times the area of the upper right triangle AOP minus the area of sector AOB. So first of all, we have to find out the area of the right upper triangle AOP. So what is the area of the right upper triangle AOP? Actually, the area of any triangle equals to the base of the triangle times the height to the base over 2. So this is the right upper triangle AOP. We'll choose the base of this right triangle AOP is AO. So the base is AO times the height. The height will be AP. So the height is AP. Why the height is AP? Because the height creates 90 degrees with the base AO. And we have to divide it by 2. AO is the radius of this circle that is equal to 2, so we substitute AO by 2 times AP. AP equals to 5.5, so we substitute AP by 5.5 divided by 2. We have 2 in the numerator and 2 in the denominator, so 2 over 2 is 1. 2 will get cancelled, and we left only with 5.5. In conclusion, we found out that the area of the right upper triangle AOP is equals to 5.5 square units. So the area of the green shape in total equals to 2 times the area of the right upper triangle AOP. So it is 2 times 5.5. 2 times 5.5 is 11. So in conclusion, we found out that the area of quadrilateral AOBP, that is 2 times the area of the right upper triangle AOP, is 11 square units. So 11 square units, that is the area of this quadrilateral AOBP, minus the area of this sector AOB will be equal exactly to the area of this green shape. So it is 11, this is the area of quadrilateral AOBP, minus the area of sector AOB. So in the next step, we will calculate the area of sector AOB. So what is the area of this sector, sector AOB? The area of sector AOB equals to the area of the circle that contains the sector, the area of this circle. The area of this circle is pi r squared because the radius is r, times the angle between the legs of this sector. The angle between the legs is this angle, it is actually 140 degrees. Okay, yeah, this angle equals to 140 degrees. So it is 140 degrees over 360 degrees. In conclusion, we found out that the area of sector AOB equals to pi r squared times 140 degrees over 360 degrees. The radius r of this circle is equal to 2 units, therefore r squared is 2 squared, that is 4. So in total, the area of the circle that contains sector AOB is pi r squared, that is 4 pi, times 140 degrees over 360 degrees. So this expression in total, 4 pi times 140 degrees over 360 degrees, is equals to 4.888 square units. In conclusion, we found out that the area of sector AOB is equals to 4.888 square units. The area of this sector AOB is equals to 4.888 square units. So what is the area of the green shape? The area of the green shape is equals to the area of this quadrilateral AOBP, that is 11 square units, minus the area of this sector AOB, that is 4.888 square units. So in conclusion, we found out that the area of the green shape equals to 11 minus 4.888, that is 6.111 square units. The area of the green shape equals to 6.111 square units. Repeat again, we found out that the area of this green shape equals to 6.111 square units. So in the next step, I will summarize the lecture. In this lecture, we found out the area of this green shape. So in the drawing, we have a circle. We know that the radius of this circle r equals to 2, and we also have inside this circle peripheral angle ACB. This is peripheral angle ACB. This is equals to 70 degrees in its size. In addition, we have also here, this is the common extent point P. From the common extent point P, we have two tangents to this circle, tangent PA and tangent PB. Again, our mission is to find out the area of this green shape. So, in the first step, we join points O and B together by a straight line. Point O is the center of the circle, point B is the point of the circle itself, therefore OB is the radius of this circle. This equals to 2 units according to what is given as the question. So OB equals to 2, is the radius of the circle, and we can implement here all 1, according to all 1, we have here the radius OB, that is on to point B, that is the point of tendency of tangent PB with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent PB will be perpendicular to the radius BO. If PB is perpendicular to BO, it means that this angle equals to 90 degrees according to rule 1. Likewise, we have here the radius OA that is drawn to point A, that is the point of tendency of tangent PA with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent PA will be perpendicular to the radius AO. If PA is perpendicular to AO, it means that this angle equals to 90 degrees according to the sum rule, rule 1. In the next step, I presented to you rule 13, and we implemented rule 13 in our drawing. According to rule 13, a central angle is twice as large as the peripheral angle subtended on the same arc. I'll repeat again rule 13. According to rule 13, a central angle is twice as large as the peripheral angle subtended on the same arc. So in the drawing we have a circle. Inside this circle we have the peripheral angle ACB that equals to theta degrees in its side and is subtended on this arc RKB. In addition, we have in this drawing the central angle AOB that is subtended on the same arc RKB. Therefore, the size of this central angle AOB that is subtended on the same RKB will be twice as large as the peripheral angle ACB. And because of the fact that the size of the peripheral angle ACB is theta, therefore the size of the central angle AOB will be equal to 2 theta. We actually implemented rule 13 in our drawing. In our drawing we have the peripheral angle ACB that equals to 70 degrees in its size and is subtended. Peripheral ACB is subtended on this arc RKB. And we also have the central angle AOB that is subtended on the same arc RKB, and therefore the size of the central angle AOB will be twice as large of the size of this peripheral angle ACB. The size of the peripheral angle ACB is 70 degrees, therefore the size of the central angle AOB will be equal to 70 degrees times 2, that is 140 degrees. In conclusion, we found out that the size of this central angle AOB is 140 degrees. In the next step, we join points O and P together by a straight line. By joining points O and P, we created 2 right triangles, the right upper triangle AOP and the right lower triangle BOP. So in the next step, we proved that those 2 right triangles can go into each other. So why those 2 right triangles can go into each other? First of all, side AO in the right upper triangle AOP is equal to side BO in the right lower triangle BOP. Here, AO equals to BO, they are both the area of the circle, therefore they are equal to each other. In addition, we have side OP is a common side that belongs to both triangles, so we can write down that OP equals to itself is a common side that belongs to both triangles. So OP equals to OP is a common side that belongs to both triangles, and finally PA equals to PB according to rule 2. And quickly on rule 2, according to rule 2, the lengths of 2 tangents from a common external point to a circle are equal. In the drawing we have a circle, and we also have here the common external point, point P. From this common external point, point P, we have 2 tangents to the circle, tangent PA and tangent PB. And according to this rule 2, they are equal to each other. That is to say, PA equals to PB. PA equals to PB. So, We actually implemented all two in our drawing. In our drawing we have the common standpoint point P. From the common standpoint point P we have two tangents to this circle, tangent PA and tangent PB. And according to rule 2 they are equal to each other. That is to say PA equals to PB. So I'll repeat again. PA equals to PB according to rule 2. So actually prove that all the three sides of this right upper triangle AOP are correspondingly equal to all the three sides of the right lower triangle, triangle PBO. And therefore those two right triangles can go into each other according to side rule. Again, the right triangle AOP is congruent, this is the side of congruent, to the right lower triangle, triangle POB, according to side rule. And from the fact that those two right triangles can go into each other, we will derive that those two angles must be also equal to each other. That is to say, angle AOP of the right upper triangle AOP is equal to angle BOP of the right lower triangle BOP, according to the rule that corresponding angles in congruent triangles are equal to each other. Those two right triangles can go into each other, therefore those two corresponding angles must be equal to each other. So if this angle is alpha, then the other angle must be also equal to alpha because they are equal to each other. Yeah, so if this angle equals to alpha, then the other angle must be also equal to each other because they are equal to each other. So if this is angle alpha, then the other angle must be also equal to alpha. So alpha plus alpha in total equals to this angle. So this big angle, we already found out that this big angle, angle AOB, is equals to 140 degrees. So we found out that alpha plus alpha equals to 140 degrees. Yeah, alpha plus alpha equals to 140 degrees. So alpha plus alpha is 2 alpha, so 2 alpha equals to 140 degrees. Here we divided this equation by 2. And finally found out that the missing angle alpha equals to 140 degrees over 2, that is 70 degrees. So this is the missing angle alpha that is equal to 70 degrees inside, and this is also angle alpha that is equal to 70 degrees. In the next step we focused on the right upper triangle, triangle AOP. In this right upper triangle AOP, triangle 70 degrees equals to AP over AO. In the right upper triangle APO, triangle 70 degrees equals to AP over AO. Triangle 70 degrees is 2.75 and it is equals to AP. AP is the missing side, so we leave it as it is, over AO. AO is 2, so we substitute AO by 2. We found out that 2.75 equals to AP over 2. Here we multiply this equation by 2 and finally found out that the missing angle, the missing side AP is equals to 2.75 times 2, that is 5.5 units. So the missing side AP equals to 5.5 units in its length. Our mission is to find out the area of this green shape. So what is the area of the green shape? The area of the green shape equals to the area of the right upper triangle AOP plus the area of the right lower triangle BOP. The sum of the areas of those two right triangles will give us the area of quadrangle AOBP. So the area of this quadrangle AOBP minus the area of this sector AOB will be equal exactly to the area of this green shape. Okay, so the area of the green shape in total is equal to the area of the upper right triangle AOP plus the area of the lower triangle BOP. Again, the sum of the areas of those two right triangles will give us the area of quadrangle AOBP, and the area of quadrangle AOBP minus the area of sector AOB is equal to the area of this green shape. So in the next step, I actually explain to you the concept of sector. What is a sector? A sector is a part of a circle. This is a circle, and the part of this circle shape AOB is a sector. So the green shape AOB is sector AOB. Sector AOB consists of two legs. The first leg is BO and the second leg is AO. Or we can also say that sector AOB consists of two radii. The first radii is BO and the second radius is AO. So the first radius is BO and the second radius is AO. and the angle between those two, on the eye, AO, BO, is theta, and it is also consists of RKB that is located between those two legs, OB and OA. Okay, so what is the area of this sector, the green sector AOB? The area of the green sector AOB equals to the area of the circle that contains the sector, that is pi r square, times the angle between the legs of this sector, that is theta, over 360 degrees. Repeat again, the area of sector AOB is equals to pi r square times theta over 360 degrees. Okay. We have already found out that those two right triangles can go into each other, and therefore they have also the same areas. Therefore, we can substitute the area of this right triangle POB by the area of this right triangle AOP. Repeat again, we can substitute the area of this right triangle BOP by the area of this right triangle AOP, because they are equal to each other. We did it, and we got the area of the green shape in total will be equal to the area of the right upper triangle AOP plus the area of the right lower triangle BOP, because of the fact that the two areas are equal to each other, you can substitute the area of the right upper triangle BOP by the area of the we can substitute the area of the right lower triangle BOP by the area of the upper right triangle AOP, because they are equal to each other. So it is the area of the upper right triangle AOP plus the area of the upper right triangle AOP minus the area of sector AOP. Again, the area of the two right triangles, the sum of the areas of those two right triangles will give us the area of this quadrilateral AOBP, and the area of quadrilateral AOBP minus the area of this sector AOB will give us exactly the area of this green shape. Okay. Again, the area of the right upper triangle AOP plus the area of the right upper triangle AOP will give us the area of quadrilateral AOBP. The area of quadrilateral AOBP minus the area of sector AOB will give us exactly the area of the green shape. So the area of the right upper triangle AOP plus the area of the right upper right triangle AOP is 2 times the area of the right upper triangle AOP minus the area of sector AOB. So first of all, we have to find out the area of the right upper triangle AOP. What is the area of the right upper triangle AOP? The area of any triangle equals to the base of the triangle times the height of the base over 2. So what is the area of the right upper triangle AOP? We choose the base AO as AO and the height of the base as AP. Repeat again, the base is AO and the height of the base is AP. AO equals to 2, AP equals to 5.5 divided by 2. We have 2 in the numerator and 2 in the denominator, so 2 will get cancelled and we left only with 5.5. In conclusion, we found out that the area of this upper right triangle APO equals to 5.5 square units. And the area of the green shape, in total it is equals to 2 times the area of triangle AOP, that is 5.5, so 2 times 5.5 is 11, and we have to subtract the area of sector AOB from the area of quadrilateral AOBP, that is equals to 11 square units. So in the next step we actually calculated the area of sector AOB. So what is the area of sector AOB? What is the area of this sector AOB? The area of sector AOB equals to the area of the circle that contains the sector, that is pi r square, times the angle between the legs of this sector AOB, that is 140 degrees over 360 degrees. Repeat again. In total, the area of sector AOB equals to pi r squared, that is the area of the circle that contains the sector, times the angle between the legs of the sector, that is 140 degrees over 360 degrees. the radius of this circle R equals to 2, therefore R squared is 2 squared, that is 4. So in total, the area of the circle that contains the sector is pi R squared equals to 4 pi times the angle between the legs of the sector that is 140 degrees over 360 degrees. So in total, this expression, in total it is equals to 4.888. So in conclusion, we found out that the area of this sector AOB is equals to 4.888 square units. And therefore, the area of the ring shape in total will be equal to the area of quadrilateral AOBP, that is 11 square units, minus the area of sector AOB, that is 4.888 square units. So 11 minus 4.888 is 6.111 square units. In conclusion, we found out that the area of this green shape equals to 6.111 square units. Okay, thank you very much.